Hello. Actually, it should be started right now, but nobody comes. You want me to start right now? Because it's kind of weird if I talk to nobody. I'm glad someone actually. I actually prepared some questions and problems. Like my plan was to walk you through the sample exam that Professor Alice posted online. I think, and I already talked to Professor Alice, and he's fine with it. Do you think that's helpful, or? Are you here for a review? Oh, all right. No one else. Right. Someone's finally showed up, so I guess we can start it right now. You uh, I forgot it. Yes. Do you have any questions? Okay. Then I'll take Yeah, actually, this is for exam 2, right? Yeah. So, weird I talk to only. Well, so he can or she can hear whatever I say. So basically, I talked to Professor Alice about this upcoming exam 2. He said this exam is about first chapter, obviously, and sorry, yes, first chapter. And from section 1.1 to 1.6 in the safety mission. So, right. So it's about up to rule of inference, but we don't deal with some, special proof problems like that. Yeah. But don't worry, even if there's some proof questions, I mean, they're not that hard. Well, well, that's true. That's true. But don't worry about it. It won't be according to him. But if he suddenly changes his mind. So basically, what I'm trying to do here is to help you guys with the sample exam that he posted online on his website, and it's one of them is from 2011, and the other is 2009. They are both actually exam 1 at that time. Yeah, I did those when I was practicing. Right? Oh, exam 1. Yeah, they're actually called exam 1, yeah. But that's about what we're going to expect in the exam 2 this time. Alright. So I'll just start it for this exam, sample exams. Like this is the first one. Because there are actually the solutions to this example, it's done in text, sample text. But if I can walk you through all this problems, I think it will be helpful for whatever it is. Like they are obviously going to be similar. Yeah. And it's about propositions, predicates, and quantifiers, right? And that's the quantifier, and finally the rule of inference, right? So let's just focus on the first problem. Can you hear me clearly? Like we are going to walk you through the whole sample test. Well, I don't know if he or she is here. There's an arrow. Okay, I can hear. Okay, all right. Oh. So this one is 2011. I think, as, to me, I think it's pretty easy.
Yeah.
Don't worry about it.
Yeah,
I mean,
it's easy. I went through all of it the last time.
yeah, I mean, my suggestion about for an exam like this is you have a nice sleep and take a bath or maybe relax. Now, to make sure that you have a clear mind, that you don't mess up with the
Yeah.
logic thing. When you're really tired, it's kind of hard for you to deal with that stuff because they are very obvious, and it's kind of like we took it for granted for a long time. But at this time, we're trying to use some formal mathematical language to define them, like deal with them. But underlying principles are very simple. Just make sure you don't make some silly mistake with them. So like I said, the first one is I don't even know how to describe it.
Okay, so for this one,
Okay.
I think what could be confusing is you might want to go through in the same order that the sentence is. So
Okay.
maybe thinking, I don't know how to do you put H in the first one,
Uh-huh.
and then say what is the code name.
But sometimes that's just not the
Yeah, I
case.
know, that's the thing.
Right.
You have to say
So
that.
you have to maybe go back to a book like this conditional proposition stuff. What is actually the English word that you use in this kind of mistake? Like here, they use when. So which one is actually the proposition before
So
the arrow, the one after the arrow?
So if it's code, then
Yes. So for this particular problem, okay, I just want to make sure that I can, because I just share the desktop, so he or she can actually see whatever is going on. And I can also see he or she. Yeah, he has a question. So the first one, we just said whatever after when is actually whatever should be before the arrow. So it's actually, it is a code that implies I don't go hiking. So we should, I think for this one, oh sorry, I don't go hiking is citation, right? So we should write B. Is that clear? Yeah, we can move on. Like it's pretty simple. I don't think it's coming from. But the second one, uh,
For the second one, I'll do
okay, the second one, let's just read the problem first. That there's among these 5 propositions, right? There is exactly one tautology and exactly one contradiction. So basically, the other 3 are just contingents, right? So why don't we just find out the contingents? Or maybe you see there's some properties for all 5 of this proposition. Like for something obvious like the third one, what if Q is true? Then now Q is false, right? Then this proposition would be when Q is true. Like when Q is true, then what is the true value of this? Yes. Then it is it's a conditional property.
Well, this is what I would do to start from
What?
Like I would just start from the first option to draw interesting.
But that can
It
take
takes
a lot of
time.
time.
I know, but I feel that like it's really interesting.
That makes sense. I mean, if we're even if we decide which one is actually tautology or contradiction, we can still use truth table to verify that. But I mean, if you want to save some time, if I'm doing it, I just find out some obvious ones that is absolutely not tautology. Where, then how about we do the truth table for this? Alright? So, basically, there's only one. So basically, there's only one variable, which is q, right? So q, location q, finally q defines non-q, right? So what is the truth table here? There are two now, and what is not q? It involves two, three.
So that's all.
You gotta remember the truth table. Remember
Oh, that
for
would be false.
yes,
The other one would be true.
this one will be true, right? So this is only false when q is whatever before is true and whatever after is false. That's the only case when it's false. So we can know there are two possible outcomes for this proposition, which means it is contingent, right? So that is not what we want, we just leave it at. Or for, how about this one? There are three propositions, three variables, P, Q, and R. We don't specify what are they. So basically, they can be anything, right? So is it possible if, like, no matter what their truth values are, they always true or, or always false? Yes, that is continuous. Like, if you said all these three true, right, then it is true. But if you said the first one true, P true, and Q true, and R false, then it's false.
But I'm thinking, if you have something completely different than
Yes.
there's no negation in any one of them, so it has to be included.
Well, I'm not sure if there's a conclusion for that, but
Because they can all be different and like there's no negation to like cancel it out or something like that.
it sort of makes sense. But I'm not very sure about it. Like, I can jump into that conclusion. Alright, so we said that this is a continuous one, right? And what about the last one? The reason I deal with these three first is these three are obviously simpler than the first two. Yeah, they're shorter, right? And more neat. I mean, so that's why I chose the three first. So what about the last one? Or is there any like
So
method we can use here?
I think the stuff over
This is
Yes.
disjunction. This is a conjunction.
So disjunction, if P is true, it can make it true, false, false. No matter what is inside of the
Is that right?
even the P conjunction
Uh,
so whatever Q conjunction P is, let's say it's false.
okay.
So
This is disjunction, not conjunction.
yeah.
Okay. So, like for things like this, did you remember like something we can do about it? like something in the printing, something outside.
Like,
Yes. Like you can check your book, like it's called distribution.
how does that work?
Okay, so it's whatever inside the printing will between the printing. Just remember. So it always equals to actually this doesn't really make it better. It really doesn't really make it better. Because you see this is P, right? So it is something like this, which is not exactly the same. So why don't we just apply the truth table?
Yeah, that's what I was doing.
So we do it here. The truth table. So P, Q, P, Q, and Q. P or Q. Right? There are all right, four rows, right? True, false, false, true, false, right? And what about the truth letter for a second? So it's true, false, false, false. Okay. Then what about the last one? It's true, true, false, false, right? Yeah, so it continues as well. So we settle that the last three are all contingencies. Because of what we know here, the first one and second one got to be one of each, right? Sure, you can do that, but if you make some observations, you can see some things really obvious. I mean, for this particular problem, I mean, if the exam changes a little bit, you gotta do the truth table. So here, you see, this is inside the principle, right? But here, the connection are two conjunctions, which means if this proposition, compound proposition, if it is true, then all the components should be true. Right? Well, the first component is Q. Well, the last one is not Q. They are off. But if you want it true, the other thing should be true, which is impossible for both Q and not Q. Yes, so this one is always false. Right? But I mean, we took a shortcut. But for a problem like this, like the first one, if you deal with the truth value, I think it's kind of good for you. But still, I mean, if you can make some simple observations, you will make things easy. So this one is a contradiction. I don't know why. So what about the second one? We already know it's a tautology, but how we prove it, or how we verify it, we don't need to prove that. Yes. That makes a lot of sense. Because P and RP cannot be both true,
Yeah.
so it's one of them is true, the other one is false, right? So the by condition for this, and we have a conjunction between them. Yeah, we can do that, but yes. All right, because we already know that the second one gotta be the tautology. In that way, we can immediately know that this is a tautology by yeah, like your way of thinking. But just to be a little more careful, we can use the truth-driven right? It's not it can be for this F and T, you can just use capital letter F and T in this one. Or maybe you can maybe the particular like for this B that can be like this. Okay. All right. I guess we can move on to the next one. Oh. Let's do it quickly. So, which of the following is the negation of the statement I will watch TV or read a book? But what is the proposition actually mean? Like, do we have something we already know? It's something or something, but not both. Yeah, it's exclusive word. So what is the negation of exclusive word? So this one, what it really means
Okay, I want to
on both.
So the negation would be I will watch and read or I will do
All right. So it's either I will watch TV and read a book, or I will do neither. Right? Okay. So this think a little bit. It's not that hard. It's nothing. It's nothing. So you just have a clear mind. You'll find it. All right. Then the fourth one. Okay, there are a little more here. Every student at IIT has a set. So the first predicate, I, is X used at IIT. So C of X is another predicate, which means that X has a cell phone. And this one is the student name. So we don't have to worry about that. So we can well, first, maybe we can settle for is it universal quantifier or control? Yes, every student is for all the students, right? Okay, so for all the students, what do you have? Okay. It's C, right? So basically means that for all the students, first he is he or she is he finds that it's not that bad. mean, that we already half of the sheet. 12. And with the last two of them, oh, there are 14. But the last two of them are specific. This is just a sample example. So this one is a little trickier, but really usable. Nested qualifier. Some believable candidates are not being supported by any Chicago list. What is So first, like there's a three. Yeah, there are three predicates. C of X is a Chicago resident. P of Y is a political candidate, and S of X and Y are X is for Y. So basically, we have to know what kind of qualifier we're using. So for some political candidate, what it really means. So there exists a candidate, right? So whatever before Y should be Y, right? And what about not by any Chicago resident? Yes, so that means for all, whatever before X is for all, but not. That's a condition, right? So basically, we can rule out the first one.
Also, the negation has to be
Yes, it's in the has in the present, right? So the second one is right.
so he's the only one who has. Because I thought it was.
Remember what we said there? Should be exists y, some y, right? For all x.
So no.
Yes, it's C or D here, right? Okay, so what about C? Or what about D? Don't forget that Y has to be a candidate, right? So there should be a P of Y. But remember, for this Y, that every X has a problem. Yes.
But C kind of wants to be correct.
But we do, write like this.
That's the thing, that's not something. The
There has to be
notation is straight.
something like this, right? Alright, but still,
Like, if we did right like this, it would be correct. But just the notation is wrong.
also we don't write, I mean, in the example in the books, we don't write C of X in another X. Like,
Oh, okay.
because S, X, and Y, you can make that X, change it by C of X. That is a little bit confusing. You are specify everything in Y,
So
right?
that should be by itself.
Yes. So D is more clear, right? If there's this is a candidate, and what it has. So what has happened simultaneously? That there's for all the residents, he voted against it. That is what he says. So that's why we say it. So what about next? we deal with this condition?
I think I would make the statement in sentence, and then I would try to indicate the sentence in English.
That is really hard. So basically, what are we trying to accomplish here? We want to know something like this, right? Not for all x, p of x, and q of x, right?
So not for all means for some, or
Yes.
for none.
We can move this negation in this direction and put it inside the parentheses and after the quantifier. So first, we can take this inside the quantifier. It really means for all x with it. Yes, exists x not p of x and q of x. Then we do the next step. Try to put this negation inside the it's like the negation of p and q is negation p or negation q. And also we have the negation of p or q is actually negation p and negation q. That's the De Morgan, so we're going to use it like a lot of times. So now we know how to deal with this stuff, right? So it's actually exists an x such that not p of x or not q of x. Which one? Oh, I already or yeah, I just get a little careful. Okay, that's it. Alright, now we are finished all the simple problems, like just choice questions. Now we have to actually write them. Okay, so this problem, for this question, the domain of x and y, you must have done some problems like this before, right? Without homework or what is your thought? Yes, we can do it. Just in the yeah. Okay, so here is x greater than 0. So what about here? Yeah, y is, okay, so y is a prime number. And end, right? There's end. And what? And. Okay, so don't forget the quantifier before them. For all x. For all x, there exists a y, right? So now can we do the translation? do anything. So what about it?
So, I'm thinking there's a prime number, I don't know what's called. There's a prime number that is, there's a positive prime number.
Are you still with me? Are you guys still with me? I'm not sure. Oh yes, great. Yeah, do you know the answer like typing? It's right. We're we need to finish this.
I believe like
We can at least finish the first. The second one is the best. You can go for it ourselves. For all x prime. Well, actually, x is not a prime. Y is prime. And don't forget, we can't use any variables in the answer. So we can use actually x or y.
for all real numbers, there's a positive prime number.
So which one? X is the positive number. Y is the prime number.
If x greater than 0, then compared to y is a prime number.
Yes, that is the principle. That is correct. But unfortunately, for this problem, we have to use, words, but not X and Y.
It's a number. If it's greater than 0, then there exists another number, which is a prime number, and it's greater than.
So how about this? So basically, we know the principles now, right? So there is, for every positive number, positive real number, right? There exists, for every positive real number, there exists a y. What is the probability of y? Y is the prime number, and x is smaller than y, right? So that is what we know from this problem. So basically, you can just say like, for every positive number, there exists a larger prime number. Is that right? For every positive number, there exists a larger prime number, right? And there's no variable c in the answer. I think that's
Is that answer on the solution?
well, that is actually not. The solution for this one is there is a prime number larger than every positive number. But I think there's a little ambiguity.
Yeah.
Right? Like there is a prime number larger than every positive number. That is not right.
Yeah, it sounds like there's only one.
Yeah. So what I write is for every positive number there exists a larger prime number. Right? Let's move on to the next one. This is a little bit. There's some twists and turns in it. So right now. Oh. This is a little number problem. This one is actually to write the argument for for this. So how many predicates are there that we are going to use?
She's a math major, she's a master education,
Okay. She is math major, right? Because there's no other people we don't have to specify the name, right? Like, so this is the only person we are dealing with. So she's math major, she's basketball women major, or okay. No discrete math, and finally smart. Yeah, that's the final thing. Okay, so can we just do like, so let's just say M is actually arrow is math major. Okay, so math major. Oh, B is she is basket weight major. Okay. So D is no discrete math, right? No discrete math. And finally, S we can use she's smart. Okay? So now, how can we use this predicate to work out the argument for?
we have to do it like this, like going down.
Yes, yes. Okay.
M or B.
M or B, right? Okay.
We need to write the reason. It's a pre.
But there going to be some other
We have to write. That's what a woman would write.
Well, I'm not sure about the standard, but but just make sure you know how to do it. Like, if you have time to down. Okay, I will B and the what?
No, not B.
Not B. Not B?
Okay. Carol is not a investigation major.
Oh, okay.
Not B.
That is the conclusion.
Well,
Not M, implies
No, M implies not B.
not M implies
not.
D implies S. Not B implies not M.
Yes. The second sentence means, E, then something, right? So not B implies not M, right? Then B implies S, right? And then not B, right? This is what we got here. Then we can have the conclusion, therefore, S. Thank you.
It doesn't even make us it tells us that. So all we have to do is translate.
Yeah. It doesn't actually ask us to
Because do not prove whether or not the argument is valid. I think this is weird. Or maybe you can, put some explanation, like put some arrows. It's basically like where you got this like argument. Which one? But if you write in this direction, obviously the first one is the first one, right? The second is the like I said, it's not that hard. This is just a simple truth table. When we start, the first one is P implies Q, right? And right. Yeah. Okay, T, F, F is RT, right? Because of the assumptions is false. Okay, so now what's not Q, right? Not Q. And what we got here? T, T. Okay. So now R and Q. Okay. R and Q. T, F, F, F.
Oh, wait, the third one. P. P and
R and
oh
Q.
no, R.
Okay. So that one's T, right? F, F, F. Okay. So now, okay, so we call it B, right? So this is B. So what about the two values for B? These two, right? Alright, F, T, 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 F, 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 right? Alright, so now the whole thing. So this one and this one. Ooh.
What is the exponent of
Good. Now, the first one.
not an F,
Oh, sorry. This is don't forget this is exclusive OR. Alright, so this is a T, right? This is F. Okay.
okay, when they're the same as
You're right. T, T, F. T, T. So, and there's something, so is this a topology, contradiction? Yes, it's a contingency, right?
to just explain why.
Right. Because sometimes it's true, sometimes it's false, so it's a contingency, right? You can either point it out which one is false or which one is true. Then we can move to the
Make it larger. The text. So it's easier
sure,
to see.
sure. Not really? This? Oh, there's our classmates, they may comment. Yeah, they can. Yeah, they can. These are the participants. They can, hear exactly what you're not hearing. So, and they also can make some comments. So I'll see what they have, have questions. Right. So now this problem. If they are logically proven.
I guess we will just trying to figure it out. So what's three ways?
I don't know. I only know one way. I mean, two ways. Either you can draw a truth table, or for this one, you see the first compound proposition have P, Q, and R, right? But the second one only have Q and R. So, what if we change P? I mean, we can decide whatever P is, right? To kind of make them different.
So they are not related.
What do you think? Like, what is your first instinct?
What is the animal?
Yes. Are they logically equivalent? I mean, if you want to prove they are logically equivalent, you have to, use the truth table to verify every single one are the same. Right? But if you want to prove they are not logically equivalent, the only thing you need to do is give a counterexample. So if you stick with the truth table, look at it like P, Q, and R, right? How many rows do you need here? 8. Okay, so T,
Go down the four and four F.
Well, just two things now.
I told you to go down the P, four C, four F, then go to T, C, F, F, T, F, F, for the Q, then T, F, T, F for the R.
Oh,
That's the technique. So F, T,
right. That's how we do it. So we can just jump into not Q and R. Okay. Okay. Balls. Balls.
Two.
Balls. Balls. Balls.
False.
Okay, balls.
that's
Two.
true.
Without P defines not Q. It's balls. Balls. Two. Balls, right? Two.
Two.
Right. All of them, all the others are true, right? That is true too. So if you do the same thing, you're gonna find out they're not logically true. Just keep on doing this truth table and stuff. But you can always find a counter example, like I said, or maybe you can, first do the truth table, and you'll see that you can manipulate this p value, the truth value of p, to make them different. You see what I mean? Finish the truth. What? They have a counter. didn't take it. So.
Is it on the?
Here it is on the solution. I just speak with two stable method. You can find a counterexample in the. You can find a counterexample in the solution that uploaded online. But I think if you are, if you didn't immediately find out that counterexample, it's kind of hard to find a counterexample. But after you finish the truth table, you know which one is the counterexample. But it takes really much time. Now, I think this one is important because you gotta verify whether this argument is invalid. How do you do that? How to prove that this thing is invalid or valid? Or in your circumstance, you know that the thing is valid or invalid. Well, you can, but that will be a bit funny. You gotta remember how this thing is valid. Yeah. How can you proceed?
It's valid if
Well, this third line,
The
not
third one?
not your Q doesn't fit. Well, if the it's equivalent to not and not.
Right.
So that's the premise.
Premises.
So it means P and Q are both equal.
Doesn't mean that because we don't know the truth value of P or Q. But if the thing is valid, this argument is valid, it really means that if the conclusion is true, then all the premises is true. And that is the only way the conclusion is true. When it's invalid, this really means that the conclusion is true, but some of the premises is false. So, when we prove that this argument is invalid or valid, we are always trying to prove that this argument is invalid. If it's not invalid, then it's valid. But how we prove this is invalid? We are trying to make the conclusion true while try to make the premises false. So how we do that? Like for this particular example. How we make the conclusion true?
by making R false.
Okay, R is false, right? False. Okay, so if R is false, then can we make any of them like false?
P is true, but R is false, then R is false.
Okay.
For the first time, P is true and R is false. P implies R, so if P is true, R is false, then it's false.
Okay.
So then that principle is false.
Okay. That's right. So if P is true, right? And how about Q?
If Q is true as well,
of them will be false.
Well, then let's make Q false.
So how about we make P and Q both false?
Yeah, but we're trying to prove that one is false.
Yeah, that's more than enough, right? The only thing we need to prove that if the conclusion is true, that some of the promises can be false. And that's it. So let's just try this, like P is false, Q is false. Then the first line is true, right? The second line is the third line. That's true.
Then if that makes it valid. I'm just trying to prove that it's valid.
Oh, sorry, I made a
So what are they not?
sorry, I made a mistake, guys. We actually want to find an example that all the premises is true while the conclusion is false. Think about it. I don't have a clear mind.
So if it's invalid, all of the things
Uh-huh. Mhm. Then it is invalid. Well, the only way it's valid is all the premises is true, the conclusion is also true. Right?
That's how you decide it's valid. It's valid only if the condition is true and
I'm not finding the proof actually.
there's if all the premises are true, then it's
Oh, right. Sorry. Okay. Now I'm here. So, if we want to prove this argument is invalid, we have to prove that when conclusion is false, that all the premises is true can make that happen. Then it's invalid. That make sense? So how about this? For all the if all the promises is true while the conclusion is false, then it's invalid. How about we try to prove it's valid? Then, if we set the conclusion false, there has to be some of the premises is also false. Then it's valid. Yes. Because in order to make it valid, all the premises has to be true to make it conclusion false. To conclusion true. Like I said, go home and take a nice sleep and think about it. It will be better. Or how about, let's just say the conclusion is false. R is true, right? Then we try to make all of the premises true to make it invalid. Okay, so what P has to be? P false. That would work actually. P is true, would also work, right? Okay, so what about Q? Q can be false, right? Then not P or Q will be true. Then all the premises are true while the conclusion is false. So we know that this argument is invalid.
that's how we
Right. Then we move on to the last one of this exam. So show step by step that the following arguments is valid by citing the rules of inference. By the way, in this exam, we actually have the first page lists all the rules of inferences, so you don't have to memorize it. But I don't know about this example. So maybe you do need to remember either. Okay. So how we are trying to prove this is valid using so basically we don't know how to start. Then we do, as much as possible. How can we deal with the first one? It's a not exist thing. Right. Move the negation sign into the qualifier, right? To make it for all x, right? Not p of x and q of x. Okay. So can we even see like moving? All right. So moving to the present. Not p or not q. By the way, I think you have to make an explanation why can you do this. Right? This is like more than yeah, this is more. Okay. So now, is there anything we can like use for the rules of inferences? Like for all of that? Because the second line is actually P of C, which means you have a like specific example.
Universal differentiation.
Okay. We can use the universal differentiation. That's how we what can we get?
Yeah. Well, we already have the system, not P or not Q. So if P, then not Q. Right? We already have the previous system, not P or not Q. And it gives another term system, P. So we have P and not Q.
For some C, right?
Yeah, for some C.
Okay, so for some C. So for every x, we have this. So we can jump into the conclusion that we can actually write it like the argument for we have not P of C or not Q of C, right? Then we combine this with P of C. Is there another rule that we can use? It's on the sheet. Yes, disjunctive. Right. Then by that, by disjunctive. We have not Q of C. It's just this is pretty much it. This is for the This is the first exam. You see the next problem is a specific proof, which is not, should not be in the upcoming exam 2 for you guys.
That's all the material for 20.
All right. So that is the whole material for exam 2. Like from the first section 1.1 to 1.6. Like Professor Alice told me that we don't deal with specific proofs.
1.1
To 1.6. Are you in a hurry?
No,
You want to go?
no, no, I'm not interested. Oh,
Okay.
why?
Because if you want, we can go through another exam as well. There's another sample exam for 2009.
Oh, yes.
Okay, so there's some people. Yeah, the session should be from 6 to 8, and I can leave before that, I suppose. This is another exam. It's in 2009, but everything's very similar. So we can move this one a little bit quicker. The first one is
It's different one.
yeah, it's actually I think when like Professor Alice or someone else who taught this course at the time, they switch the materials. Like
the
first
order.
yeah,
Order.
switch the order, yeah. But basically the materials are the same. Like I actually talked to Professor Alice. He told me that this sample exam 1 is actually what you're going to expect in this exam 2. So that's why I use this exam 1. So the first one, same problem again. But this one we have PQ and R. Well, still we can use the truth table, right? Again, do I need to like go through all the truth table again? Anybody with me here? Anybody with me here? Like, do I need to like go through all the truth table again? I mean, all these things are recorded, and I think my director is gonna upload it to the YouTube so you guys can review it if it is necessary. I guess it's not necessary. The first one is just write down the truth table. We're going to find out there are some difference between the truth values at last that you can show that they are not actually not logically equivalent. For the second one, same thing again, right? So PQ and R, just fill out this truth table. We can actually do this one. So now we have P exclusive in or Q. This is the right false, false, true, 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 false. What about pure condition R? True, true, false, false, true, true, false, false, true. And now we're dealing with whatever is here. So this implies this. So whenever the the assumption is false, it's automatically true. So we don't So it's asking when the truth value, which rows of the truth table is false. Third. This one. So the third problem in an original statement is if 1 plus 1 equals 3, then 2 plus 2 equals 4. How we deal with this problem? I think we can make the assumption P, right? The conclusion P. Then what is the contrapositive of the original statement?
Contrapositive means if 2 plus 2 is not equal to 4.
Okay, so basically it's not Q implies not P, right? And it has the same truth value as the original statement.
Oh, but wait, false true is true.
Right, this is true until Q is not true. So what about the second one? What is the converse of the original statement?
I don't remember.
It's Q implies P, which is the converse.
It's false. It's true implies false, it's false.
Right, it's false. Finally, the inverse. Inverse is not P implies not Q, which is
True, false, and false.
yes, it's also false. So not that hard. Just remember what is the converse, what is the inverse, and what is the counterpart. So now write the negation of the following statement. I will go to the movie or read the book, but not both. That is actually from last sample we had. This is exclusively order, right?
Does it mean that the representation in that?
Yes, in English.
This is exclusive or?
So what's its negation?
This is our vote. This is our vote.
Is that the only thing? Think about it. I will go to the movie or read a book, but not do both.
I can't remember what the negation method is.
But just think about it. Like, what is the, you know? Well, can you like switch the sentence into something that more understandable? I will go to the movie or read a book, but not books. So basically, you're gonna do one of them, right? Exactly one of them. So what is the, the negation of only do one, not do both? That is one case. Is there any other? Right. So basically, the negation is not do anything or do both. Think about it. For two things, go to the movies or read a book, there are only four scenarios. One is go to movie only. read the book or do both or do nothing, right? So the negation gotta be the other two scenarios, which is
Both and nothing.
right. So how you describe this in
Oh, okay. I will go to the movie and read the book. Or I will do not.
English? So we can, maybe we can say like, either I will go to the movie and read a book, or I will do nothing, or will do neither. So now, like I said, I think this is is the Fourier argument valid? So, like I said, we are trying to first prove that this is invalid. Trying to. If you didn't get it right, then you know it's valid. Right? So how we like trying to prove the thing is invalid.
This is pretty simple, so I don't have to do it backwards.
Okay.
Not really. It doesn't even ask us to explain.
No.
So not P is false, and P is assumption, so it's false. So, like P2 is no P type Q. P type Q. It's not necessary. It's invalid.
Yeah, it's invalid. But like I said, using my way, I think it's really we can try it, right? So let's just assume the conclusion is false. Okay, so Q is true, right? So if Q is true, let's make all the premises true. Then you see, if not P is true, then P is false, right? And also P implies Q is also true, which means two true premises leads to a false conclusion. So that would be invalid. So what about this one? Okay, so we make the conclusion false. P is true. Q is true. Okay.
P implies not Q, so it's true implies false.
Okay. So now we know the only way we can make conclusion false is we'll have some false premises, which means this argument is actually valid.
False. This is valid.
Yes, it's invalid. I can say it again. The only way to make a conclusion false is to have a false premise.
So it doesn't matter. So it doesn't matter if the conclusion is true or false. Well,
Oh, the valid thing, it doesn't really matter if the conclusion is true or false. If a valid argument can lead to a false conclusion if the premises is false.
oh, so it's like the same thing as the truth table.
I don't really understand what you mean. I mean, for this argument valid, the definition is only true premises leads to true conclusion.
Oh, so authentications like false or something. False.
The thing we're trying to use here is the contrapositive of this principle. Like I said, only all the premises are true leads to the true conclusion. So what we are trying to do is we have a false conclusion.
Oh, so there must be a false input.
Yes. That's we are trying to prove here.
Well, you already set the conclusion false, and there is a false input.
That is valid. Well, maybe you can write it down and think about it. Or maybe you guys can review this whole session after my director uploaded on the YouTube. But I don't know where to find it. You can find out in the ARC website, I guess. Think about this. Oh, this problem, the seventh one, this is the same thing with the last example. The problem 2 and the last example, last sample test. So we are doing, some of the items are actually exactly the same, like this one, or this one is very obvious. It's contingency, right? Yeah. So basically, what we do is B and E, and they are the same as the last, sample test. But there are a little difference, like the last one. These two are conjunctions, but this one is a D conjunction. D junction, sorry, T junction. So this is a P or P or not P, right? Yes. Like either one gotta be true. So it's a topology. So this one's gotta be contradiction. But we can use truth table to verify it. Or maybe not, maybe we don't need to, because here is an and, right? So in order this thing to be true, that both sides has to be true. But here we have P and not P. They cannot be, simultaneously true. This is gotta be a contradiction. Okay. Well, this one's even simpler. Define. This is a predicate that has two variables, x and y. So x plus 2y equals to x, y. And we know that C is the set of all the integers. So what about 0, 2? Is that true?
No.
Yeah, so 0 plus 2 times 2 equals 0, which is false, right? What about 1, negative 1? Yes. Integers from negative 100, negative 1, anyway. 0, 1, negative 1, 2, negative, they are all integers.
Yeah.
1 plus 2 times negative 1 is actually negative 1. So now we have some nested solution. Oh, that is this is quantifier. So there exists a y, which is an integer such as p 3 y. That's true.
Where P y is 3.
Y is 3. let's just write it out. So x is 3, right? So 3 plus 2y equals to 3y. Equals to y equals 3. So there actually is a y. So it is true. What about the last one?
No. No.
That is false.
How do we prove it is false?
Like I said, we can write it out. Right? So what about for y and x? There are just arbitrary numbers, right? So x plus 2y is x and y. If you want to prove it's not true, then we can have some counterexample. But a counterexample is not that easy to find.
Are you find a formula for y?
Yes, that we are trying to do. We can, like here is for every y there exists an x, right?
Okay.
So every y there exists an x. So we can express x by y, right?
Okay.
So x minus x y equal to 2y.
Negative 2y. Negative 2y.
Oh, sorry. Right, that's right. So factor out x. 1 minus y is negative 2y. So x is 2y over y minus 1, right? So if this proposition is true, then whatever y you plug it in as has to be, an integer, right? So what if like y is 4? Then x is a over 3, which is not an integer. So this is the current example. Or the simpler example is if y equals to 1, then you see it becomes x plus 2 equals to x, which cannot be true for any x. So this is false.
Prove this kind of question, we just find a counterexample.
Yes, to prove something is false, you only need to find a counterexample. But I don't think in this exam you actually have to prove something. I think that's going to be the next. So now, the nice one. Okay, there are 3 more. The nice one, write the negation of the following proposition so that all the quantifiers are to the left of the negation. So it's like no, not for all, not exists, and there's no negation in front of the parentheses. So not is x such that p of x is to q of x, and not are. What's the next step? The first step.
So, no,
For all x, okay. Not for this thing, right? So we have for all x, we have to put the negation sign into the parentheses, right? So what we got here? Remember, for p leads to q is always the same as not p or q. You gotta remember this. Otherwise, you can't do this negation because it's kind of hard to put a negation for that conditional proposition, right? So, like we already know that p implies q is not p or q. Then what is in the parentheses?
Px or Qx.
So not not, right?
Yes.
Or Q of x and not R of x. So which is for all x. Now we can apply the De Morgan's law, right? Because the premises is
Just T and not Q. The negation is not T or Q, but is
Q of x and not Q of x and not R of x. Right? So it's for all x, P of x. We use the De Morgan law again. And not Qx or Rx. And that's it. The negation is in the premises and in the quantifier. So that's done. Anybody with me so far? Repeat. So this one, the associated probability of multiplication of a set of real numbers is that you can multiply three real numbers in arbitrary order and get the same result. We are trying to express this probability as a quantified case, as we are using a quantifier. There are three numbers, right? So we can make them x, y, and z. Right, then what's next? The next is a crucial. What is the associated probability of multiplication? It's actually x, y, z. First take x and y equals to x times y and z. That is the associated probability of multiplication. So the arbitrary order for all the real numbers. How can we use the context?
for all x and
For all x,
there is the y and z.
there exists a y and z because x, y, z can be arbitrary.
For all x, y,
Yeah, for all x, for all y, for all z. X, y, times z is actually x times y. Of course, x, y, z are. That is the domain of this concept.
That's it.
That's it. So finally, the last one. This is the last problem that is in the scope of your upcoming. Because others are just specific proof problems. We don't expect it in exam 2. So the last one is there are three predicates f of a, which is a is a finite set. as A and B is A is a subset of B. You guys familiar with set theory? Like, what is a set or what is a subset?
I'm not sure.
Like, just a smaller side, a set inside B than A. If A, this is the subset of B, but that's not important in this problem. Let's just say A is a subset of B. That is the S predicate. And the domain of every multiplier is the universe. So basically, domain is everything. You don't have to worry about it. So translate the following statement into concise, meaningful English sentences. So now we here have a negation. Basically, it's not a case, right? We can now say it's not a case. That's something. First, we can forget about this negation for a second. Like, what does it mean?
Well, actually, a finite set is the subset of
You think that it is? A finite set. So here there is a A, right? There is exists a set A, and there exists a set B. Well, not if A means A is infinite, right? Infinite. And the B means B is finite, right? So B is finite. And SAB means A is a subset of B, right? So basically, without the negation, it really means an infinite set is a subset of finite set. Right? So which is not possible. So using English, this really means what? Yes. This is infinite A. Okay? This is a finite B. This means A is a subset of B. Well, not this. Well, not exist A and B. Okay, so for every A and B, not, right? For every A and B, there's not an infinite set A, which is a subset of a finite set B. To make it more precisely organized. So we have to use English. Sure. Go ahead.
Only right we use bracket.
But
B is the subset of A. If, no, A, just A.
Remember what we have here without the negation. It really means there exists A and B, right? And A is infinite, while B is finite, and A is a subset of B. Maybe you can draw a little picture here. This is A, this is B. So A is a subset of B, but A is infinite. B is finite. But this is not the case. Well, how can we not this?
So A is finite, B is infinite, and A is subset of B. It's not directly.
Here we have a or.
How do we transport?
So we can write it like this. We just not whatever we have without the condition. So basically there doesn't exist a finite set which is a subset of sorry. There doesn't exist an infinite set which is a finite set subset. Maybe we can use some other words like no finite set contains an infinite set. Yeah.
No finite subset. So that's how we translate it. So they're not literally translate process.
Right.
Isn't this like that?
He's more concise. And he expressed the right meaning, right?
Yeah. So, how can you translate the statement contains or sign?
Then or. Let me see how.
Is this translatable? So meaningful.
It becomes very hard to translate if you put a negation in the front. Okay. Like F A or not F B or not S A B. Now there are too many scenarios. Since there are so the best we can do It's like for all A and all B not. If it is easier to translate them, we can deal with that. Alright, that's pretty much it. Oh, thank you. I'm pretty sure that you guys can find it online on YouTube. You can check. There must be something on the one side of the arc. So if you want to, see it again, you can find it there. Oh, thank you. That's it. Good night. Ah. 稍等。